This is the fourth segment in work, energy, and power. And here we're going to talk about another rate. We've talked about a number of rates over the course of the year, velocity, acceleration, there have been some others. And today we're going to talk about the rate at which work is done. And the rate at which work is done is given the term power. And we can also think about it in terms of the change in energy. Because if we remember, work is changing the energy of a system. So when you do work on a system, you're changing the energy of that system. And so our equation can come in two forms. We can say it's the work per unit time or the change in energy per unit time. And our units for work are what we call watts, W-A-T-T, or joules per second. And one derivation you might find useful with this, if we say that our power is work per unit time, and we know that work is equal to force times distance. And so looking at it from this respect, if you have an object that's traveling at a constant velocity, that velocity can be described as dt, and so when we have objects traveling at a uniform velocity, we can also find the power by multiplying the force times the speed of that particular object, or FV. And again, the units for power here are watts. And you've probably heard the term watts when talking about light bulbs, or being used to describe light bulbs. And it has the exact same meaning. When we're talking about wattage of light bulbs, we're talking about how much energy they use up in a given period of time. So a 65 watt light bulb uses 65 joules of energy per second. It converts 65 joules of electrical energy into thermal and radiant energy each second. So if you have a higher wattage light bulb, it's converting more energy per unit time into heat and light, and since you're getting more light per unit time, or more light in each second, that light is going to seem brighter because there's more of it. Now those light bulbs, they convert a certain amount of electrical energy to light and heat, but realistically, particularly our incandescent light bulbs, the light bulbs with the filaments, are not what we call efficient. And when we're talking about the efficiency of an object, a system, an item, whatever it happens to be, a light bulb, what we're really talking about is the amount of useful work in compared to the amount of useful work out. And so if you supply 100 joules of electrical energy to a light bulb, but you only get 20 joules of light out, that's only about 20% efficient, because only 20% of the electrical energy is actually getting converted into the energy that we want. And so the lower the efficiency, the more waste energy there happens to be.